Here we're going to discuss something called the principle of moments, which is also called Varignons theorem. So in your book you might see it as principle of moments, or you might also see it discussed simply as Varignons theorem. Now I've actually taught you the principle of moments, or Varignons theorem, actually during the course of this course so far. I just haven't called it that. But since you have a section in your book that's titled that, I want to go ahead and formalize it, show you exactly what we mean, and then work just a couple of quick problems. But basically you already know what it is. Now, how do you spell this guy? This is how you spell it. Varignon theorem. I'm sure I'm mangling that when I try to say it out loud, so I'm just going to prefer to call it the principle of moments. I could write it down, okay, but it's very simple to understand, so I'll just verbalize it for you. The principle of moments says that the moment of a force is the sum of the moments produced by the components of the force, okay? By the components of the force. I'll say it again. The moment of a force produced about some point is just the sum of the moments that are produced. If you take that force and decompose it into its component forces and look at the moments produced by those. So the sum of the moment of a force is the sum of the moments produced by the components of the force. Now I've actually used that several times already to help you solve problems, to teach you how to solve problems, because when you start getting into math, you're dealing with vectors and decomposition of vectors. It's natural for you to think of it in terms of components, and it makes total sense. If the components of the force can vectorially be added together to give you the original force, then they're equivalent mathematically. So whether or not you're working with a single force or two vector forces that form the components, they're exactly equivalent. So it makes sense that the principle of moments is true. We just haven't actually formalized it like that. So to kind of solidify it just a little bit more, I want to draw a quick picture to show you what I'm talking about. So for instance, let's just say, this isn't going to be really a problem as much as it'll be a little proof. Let's say we have some point of origin O, and so we're going to end up applying a force through some moment arm there. And the moment arm that we have here in this case, we're calling it R. So it extends from the point of rotation there. And then at the tip of R, I'll go ahead and switch colors for that. So this could be a metal beam or a piece of wood that's this long, pointed in this direction from the tip of the arrow here. And right at the end of the board, or whatever you're thinking about, you have some force. We call it F. So they're both vectors. Here's R vector, here's F vector. The F vector is applied at the tip of this vector R, which is given by the drawing, oriented like that. Now without thinking about it, you know that if this is a rigid beam and if this is nailed into the wall, if I apply a force, even though it's at an angle like this, it's still going to tend to rotate the thing in general like this. But and in fact, if I asked you to calculate the moment without using any components or anything, I mean, you certainly could do that. Basically, what you need to do is figure out the component of the force acting perpendicular to this guy, or to the moment arm there. So you could, if you could somehow mathematically calculate, okay, this is the vector here. If I only wanted to figure out what the component of it was that's acting perpendicular to this perpendicular component would be the part that spins it around. Alternatively, we've talked about the fact that you could use the full-blown force and find the perpendicular distance to the line of action. So this force line of action is going like this. So if I draw a dotted line this way, here is the line of action. The perpendicular moment arm to the line of action would be this distance from here to here. So I could use the full-blown force multiplied by the perpendicular distance, that'll give me the moment, or I can use the full-blown distance and just find the perpendicular force. We've gone through this many, many times. That is how you do it, just by using the original force and the original distance vector r. But this kind of problem is ripe for figuring out components to help you figure that out. Because maybe figuring out this perpendicular force here is difficult. Maybe figuring out this perpendicular distance here to the line of action is difficult. Depending on what you're given in your problem, that could be hard to figure out. So the principle of moments comes to the rescue, and basically what it says, essentially what you want to do whenever you're splitting a force into components is you want to make it into a vertical component, which will lie in this direction, and then you want to have a horizontal component like this. So the vertical component really is going to be this guy, so I'll draw it like this. And then the horizontal component is going to be like this. So the way that you can justify to yourself that these are the proper components is this projection coming down is the tip of this arrow, and the projection of this going across is the tip of that arrow. So basically what we do is we say that this horizontal thing is called F sub x, and we call this vertical thing, this vertical component of the force, F sub y. Now these are vectors, just like the original was vector, so you know that you can take this plus this vectorially, and you can just see it drawn on the board here. The vector result is actually the red vector here. So it's important to note, I've said it already, but the red vector being a single vector and the sum of these two blue vectors as a pair, they are exactly equivalent. The universe doesn't care if I apply one force oriented at an angle or if I just apply a vertical and a horizontal force separately. The actual behavior of the moment here is going to behave the same. In other words, if this is a metal rod, I can tie a rope to it and I can pull at this angle with this force F. That's going to produce some moment, some turning action, right? Now, if I throw that away and say, okay, instead of one rope, I tie two ropes, a horizontal rope and a vertical rope. I pull the horizontal rope with this much force, and I pull the vertical rope with this much force. So now I have two ropes I'm pulling like this, producing this pair of vectors, vertical and horizontal. That's going to produce exactly the same moment or turning force because they're equivalent to one another. So how do we mathematically write that? The way we mathematically write that is we have to say that the moment about point O, which is what we're trying to find, in general is R, this R here, crossed with big vector F, right? That's in general what the moment is about this, R cross F, which is the red vector, okay? But we already said that this vector F is the vector sum of these scalar components here. So the way that you figure that out is you say, it's going to be R cross, but F, big F vector is really the sum, an X component vector plus a Y component vector, right? The X plus Y, this is an X vector in the X direction, this is a Y vector in the Y direction, and these are two vectors, we sum them together. We're saying it's exactly equivalent to this, so I can replace it in here. So far we've changed nothing. All we're saying is that the moment about the origin can be written as R cross F, or it can be written as R cross the vector sum of these blue vectors here, which is exactly what I verbally said on the board, all right? So how do we proceed then? When we have a cross product, we have R cross the sum of these vectors. We can distribute this cross product in just like you can do for anything else. You just have to keep the order proper. So what you have here is R cross Fx, like this, vector, plus R cross Fy vector. So far this shouldn't come as a surprise. This is the moment about O due only to the F component of the force. It's just this vector crossed with R. That gives me the moment due to this one. Here we have R cross Fy, so it's the moment due solely due to the vertical force. Now notice that Fx and Fy, they're pointed at 90 degrees like this. So the Fx vector is going to tend to rotate the thing clockwise like this, which if you remember from your sign convention should be a negative moment. The Fy vector is pulling up, so it's going to tend to rotate the thing in the counterclockwise direction, which you should remember to be a positive moment. So they're basically fighting each other. Which one is going to win? Well, it depends on the actual numbers here, but the way we've got it drawn, the Fx vector here certainly looks to be bigger depending on the way that I've drawn it here, but that's just because that's the way I've drawn this vector F. But essentially, the way I've got it drawn here, this is going to fight against this. The algebraic sum of these moments is going to determine which direction the thing's actually going to turn. So now that we've got everything drawn in terms of components, how do we go further from this step here? All right, R cross Fx. How do we do that cross product? Well, let me draw a few things to show you here. So we're trying to find the moment due to the X component here. Now remember, moments and cross products really are essentially, you're going to multiply these two things together, but you only care about the components that are perpendicular to one another. That's what a cross product is, okay? So if you think about it, this horizontal force, if you extend the line of action this way, and then you look at this guy here at 90 degrees, then basically what you're going to do is you're going to take the force here, Fx, and you're going to be multiplying it times the perpendicular distance that goes from the point of application, or the rotation point, up to where it intersects the line of action at 90 degrees. So it's going to be this times this distance, because these are perpendicular to one another. You only want to use the perpendicular In this case, we're using the perpendicular distance here. All right, that's just how I'm having to draw it here. So essentially, what you've got, and we also said that this is going to be pulling it and rotating it this way, which is clockwise, which is negative. So this cross product is going to be negative fx times y, where I'm defining y to be, just for the sake of the drawing here, this vertical component here, this perpendicular component, let's just call it y. It's really the perpendicular projection of r in this direction, but we're going to relabel it y. So what we have here is f of x times this distance, we're calling it y. It's got to be negative because it's going to rotate it this way. Then we want to figure out what is the cross product of these guys. What does the moment do to the y component of the force? So again, we have to figure out the perpendicular component of this guy. So if we take this guy and extend the line of action of this force down like this, you know what? Let me switch colors to make it clear. If I extend the line of action of this force down, then I want to figure out where does this guy intersect at 90 degrees. So essentially, you use the distance here. We're going to call it x because it's horizontal. It's the distance from the point of rotation where it intersects the line of action at 90 degrees. That's what we've been doing in all of these problems so far. So essentially what it's going to be is it's going to be the force F sub y times this horizontal distance x. And it's positive because this arrow is tending to rotate it counterclockwise, and we've been saying from the beginning that counterclockwise rotations, we're taking them to be positive in our sign convention. So just like we said at the beginning, we have two moments. This is the moment due to the x force. This is the moment due to the y force. They're fighting each other. One's negative, one's positive, because they're both tending to rotate the thing in different directions. So this is essentially, if you were to blow it out, this is what would be the moment about O due to this force F. Now, this, of course, is deriving it in terms of blowing this out into components and basically showing you what the principle of moments is. So in words, to circle back, Varignons theorem or principle of moments, a moment of a force is the sum of the moments produced by the components of the force. And that's exactly what it says. The moment of the force, R cross F, of course, if you know what R is and you know what F is, just cross it and then you get the answer. But it can also be written as the sum of the moments due to the components. This is the moment of the x component, this is the moment of the y component. And that's just illustrating in words. Now to do something and actually learn something from it and do a quick problem, we're going to solve this easy little problem here. It's not very complicated, but it just, again, it comes about because it gives us practice here. So what we have is a point O, and we have a metal bar, and it goes up at 45 degrees. We have dimensions here of the different segments of the bar. At the tip of the bar, we have a force at 300 newtons. Again, it's angled 30 degrees from the horizontal. And we want to figure out what the moment of this force is about the point O. All right, so if you know everything about your problem, then the easy way to do it is you figure out what your vector is, F, in terms of ijk. You know what the magnitude is. You know what the angle is. So you can figure out with cosine and sine, you can figure out what the vector representation of that guy is. In fact, we're going to do that as part of our problem. Okay? And then if you don't want to do anything with components, if you want to just figure out what the moment is about here, then you need to know what the r vector is, which is the straight vector from the point of rotation to where the force is applied. You need to know what this vector r is. Now you can figure that out. You can go and there are ways to do that. I mean, I could actually solve it that way. Let's find an r vector that goes from here all the way up to there, because you know these dimensions. You could figure that out, and then you could do r cross f using the matrix, and you would figure out the moment. Okay, so there's more than one way to solve a problem, but since we're doing principle of moments here, the goal is to show you that you don't have to do it that way. You can break this force up into components, all right, and just find the moment due to the x component of that force, the moment due to the y component of that force. Because of the scalar nature of what we have and the two-dimensional nature, it's going to be easy to do that. Figure out what the moment is due to x, the moment is due to y, and add them up. So let's do it that way. All right, so what would be the x component of this force? We would call that x, f sub x. What's the x component of that force? Well, it's 300 cosine of 30. That's going to chop it down this direction, and it would be pointing in the positive x direction. So it would be 300 times the cosine of 30 degrees. And when you take this and multiply 300 cosine 30, you get 259.81 newtons, because that's in newtons. And what if I wanted to find the y component of this force? F sub y, it's 300 times the sine of 30. 300 times the sine of 30 degrees. So when you do this, sine of 30 is 1/2 times 300, you get exactly 150 newtons acting vertically, because this guy projected up would be in the positive y direction. So we have the x component of F, we have the y component of F, we know the x component is pointed this direction, we know the y component is pointed this direction. So now all that really remains is we want to figure out what the moment is just due to this horizontally oriented x force, figure out what that moment is, and then we want to figure out what the moment is just due to this vertically oriented y force. We'll get a separate moment, we add them together. This is very similar, it's the same thing as what we've been doing in a lot of other problems. We just never really called it the principle of moments before. Okay? So what we're going to have, essentially, if you think about it, is the moment about the origin is going to be the sum of the moments caused by these forces. So if we start with the y force, okay, which let's call it, let's just put my pen here and show you that this is vertically oriented up. Which direction is it going to tend to rotate this? The vertical force is going to tend to go counterclockwise, so it's going to be positive moment, and what it's going to be is it's going to be this force, okay, times the x direction coming down over here. So what we're going to have is, it'll be the y force times an x value, or an x distance from the origin all the way out to where it intersects with, in a 90-degree fashion, this vertically oriented force there. And then this is the moment due to y, the y force. Then we're going to have the force in the x direction, which is this guy. And which direction is he going to tend to rotate? If you pull this way, he's going to tend to rotate the whole thing this way, which will be a negative moment. So we have to stick a negative there, and it'll be fx. It'll be pulling this way, and we're looking for the 90-degree distance down to the rotation point, so it'll be y like that. Just make sure you understand essentially what's happening is you have a vector, okay, well, I need to use a different color to make it clear, I think. Basically, this force vector is going to be, here's the vertical component, and here is the horizontal component, right? So this is f sub x, whoops, and this is f sub y. So when we're finding the moment due to y, this guy here, the way you do it is you take the line of action. Well, there's more than one way to do it, but in this case what I'm going to do is take the line of action, I'm going to extend it down so it makes a 90-degree with a line. Well, it shouldn't be this line, it should be really this one. But until it makes a 90-degree angle with a line coming out of my rotation point. So this distance right here, this is what I'm calling, or this distance right here, this is what I'm calling x, okay? Then I can also take this line of action and I can extend it over here, right? So that it makes a 90-degree angle with a line coming out of that guy. This is what I'm calling y. And then this whole, which is this distance here, so I'll make it clear, I'll put the y on this side. And x is this whole distance down here. I'm not going to write it on the board because it'll make it cluttered up. So you just need to be able to chop through the BS here and just look and say, this force is acting this way, I need a perpendicular distance. This guy's going this way, I need a perpendicular distance. And that's what's going to actually drive the thing around. So the moment about the origin, Fy, we already know what it is. It's 150 newtons. And now we need to find this x value here. But this x value is 0.4 meters plus this distance here, this little distance here, which this distance is given as 0.3 meters, but you know the angle is 45. So 0.3 times the cosine of 45 degrees. Make sure you understand that. This is the distance from O all the way out to this green line here. It's 0.4 plus this little distance, which is this 0.3 times cosine of 45. Then we have the minus sign here. And then what we want to do now is just figure out this distance here. So we have f sub x, which is 259.81. And then what we need to do is figure out what y is here, because that's the only distance we care about. This isn't relevant, so to get this distance here, it's 0.3 times the sine of 45. 0.3 sine 45 degrees. So basically, this is this distance, and this whole thing is this whole distance right here. So what we're going to do then is say we got 150, and on the inside, whenever you take 0.3 times cosine 45 times plus 0.4, 0.612 minus, and then over here 259.81, and this 0.3 times sine 45, you get 0.212. And I'll just switch colors and write the final answer here. What you get is 91.82 minus 55.11, and then you get 36.71. And the unit, we're dealing with newtons and meters, so the unit is Newton meters. Now notice that I kept track of the signs of everything here because I looked at this and I said this is going to make a positive moment. We looked at this and said it's going to make a negative moment. That's why the negative sign's there. So basically this number 91.82, this is the moment in the positive direction caused by force y. This number here is the moment caused by force x, and it's negative because it's tending to spin it the other way. These are fighting each other, the algebraic sum of which gives us a positive moment, and a positive moment means the thing is really going to rotate in this direction like this at the end of the day. Okay, so the answer is 36.71 Newton meters. So it's not really rocket science. I mean, I've actually kind of taught you this as we go along. I think it's kind of silly to kind of withhold something like this early on in a mechanics type of situation because essentially you're going to be doing a lot of problems like this whenever you're splitting things into components. But a lot of times in your book, you learn about moments and you calculate them in really hard, convoluted ways, and then they teach you, oh, you can just break it into components. Everything's easy now. So I've kind of done a little differently. I've kind of taught you this as we've gone, but we're just solidifying everything, calling this principle of moments so that you understand that it's not anything to be worried about. I've got another problem I want to work with you just to shore this up a little bit, give you a little more practice, so let's go off and do that one right now.
Learn anything at mathandscience.com.